Hi, all. I'm Joe Manlove. I was asked to provide some historical context for where pi comes from by Lisa. So I'm going to try to do just a little bit of that. I'm going to try to keep it short and kind of hopefully cool. So, first of all, pi is defined as the number that you multiply the diameter of a circle by to get its circumference. So in my picture here, you'll see I've got a green line and a orange circle. If I take the length of the green line, which in my case, I think is actually 10. So I think I set this as 10. So I've got the green line is 10. I multiply by something and get the length of the orange line. So the reason you might want to do this is if you're interested in figuring out how far it is between two cities, you might just make a mark on a wagon wheel and you could just count every time the wagon wheel comes up. The thing is that if you know how wide the wheel is, it's not really super straightforward somehow to figure out how far around the wheel is. It's like actually kind of puzzling. So historically, the Greeks had some thoughts about this, and like it kind of didn't go that well actually to begin with. The Greeks weren't initially really sure whether there were numbers that weren't fractions. So they kept kind of trying to figure out a fraction for this. So you can pretty easily, like with a piece of string, you can figure out it's about 3 and it's a bit more. If you spend some time like measuring more accurately, you can figure out it's like 3 and a bit less than a quarter. If you do some more fiddling, you can figure out it's about 3 and a seventh, which is kind of weird. So for a while, people used 22 sevenths as an approximation of pi. It's not actually super good, but it's okay enough. So like if you're trying to figure out whether you can use a certain size chainsaw to cut down a tree, you can basically take the diameter at breast height, divide by 3. That'll give you about the bar length you need, like good enough, right? 3 is good enough for most cases. If you're building something, you might really need that level of precision that you get out of like 3.15 ish. That'd be maybe good enough. If you're doing precision engineering, you really need better pi though. So here's where we get better pi. This is a method courtesy of Archimedes called the method of exhaustion. So I'm going to turn off my little diameter and I'm going to turn on a triangle outside. So I'm building a triangle that just barely encapsulates my circle. And I'm going to build a triangle that just barely fits inside the circle, right? So these are regular shapes, which means that all the sides are the same length. So these are equilateral triangles for those kind of with some math chops. Without it, don't worry about it. It's just a triangle where all the sides are the same size. So my next step, right, is to say, well, that's pretty crummy. If I look here, I'll see the blue one would give me a number that's about 5.2 for the value of pi, and the green one on the inside would give me a value that's like 2.6. So all I've gotten from this right now is that the number for pi is somewhere between 5.2 and 2.6. That's not a very good estimate. I can do better than that with friggin' string. So we're going to bump it up. So here's a square, one square that just barely fits inside, one square that just barely fits outside. And from this, we can figure out that our upper bound is 4 and our lower bound is like 2.83-ish, right? Again, not bad. Also, I could have figured that out with string. So let's bump it up one more. So now I've got a pentagon on the outside and a pentagon on the inside. See that our bounds now are getting closer, right? I've got 3.63 for the upper bound and 2.94 for the lower bound. I'm going to stop reading these. Let's just see what happens. So that's a hexagon. That's a heptagon. So hexagon, 6 sides, heptagon, 7. I'm going to stop knowing the names pretty quick here. So at 7 sides, we've got that it's certainly in the low 3 kind of range. An octagon, something-agon, right? So we're just going to keep going. All right, so here I've got 13 sides, and I know it's between 3.11 and 3.2. just keep cranking. So we can see that we're having less and less extra space in between the green and the blue, right? So when I get up to 20 sides, I've got that pi ought to be between 3.167 and 3.128. Let's crank this thing and let's see how far it'll go. So let's just push this up into, let's go for a nice even hundo. So at 100, so that's a 100-sided shape drawn on the outside and a 100-sided shape drawn on the inside. You'll notice I can't really tell the difference between these without zooming in pretty far. So there's kind of the error, right? It's just that little extra there. And here I'm at 3.14, so I'm between 3.142 and 3.141, right? So I've got 3 decimal places locked down. Let's go up to, perfect, 157 places. So at 157 sides, I know that pi is between 3.1413 and 3.1420. If we continue this, get at 200 sides, I've got up to 3.141 now. Now I'm sure that the next digit's 1, and I'm still not sure the digit past that, right? The fifth digit here is someplace between 4 and 8. So let's crank this puppy and let's see where we can get. Okay, so I just jumped to 2,000 sides. You can no longer see the circle at all. And now it looks like I'm certain up to 3.14159. And the next digit is someplace between 1 and 5. Let's just for kicks, let's see how long it takes to break Desmos. Oh, we broke Desmos. Okay, so 2,000 Desmos was good. Let's see if we can get, 10,000 out of this. Okay, 10,000 decided not to. Oh, 10,000 looks like it worked. It looks like, yep. So we're not happy about graphing it, apparently. This may not have more than 10,000 elements. I'm guessing that means that I could put 9,999 in there. And I've got, okay, I've got 3.14159. The next digit's a 2. And then the next digit is either a 6 or a 7. This is cool. Let's see. I want to go back to my kind of original here. Oh, God. Oh, God. Okay. Let's see. So my original was 20. And so I just want to show that. Oops. No, thank you. So let's show up to, say, 25 by 1s here. Okay, so there we go, right? We're kind of approaching, right? We're converging on knowing a value of pi by drawing more and more like finer and finer polygons in here, right? Every time we get a little, like one more side on our polygons, we get to know just a little bit better what pi is. And if we build lots and lots, we can get a good approximation. Should be noted, this isn't actually how we approximate pi these days. This is kind of an old school method, but you could see that you could do this method in the sand with a stick, which is actually how they did it. And they got to, I think, 4 or 5 decimal places, which is pretty freaking good, considering that you're having to measure things with a stick and not use a computer. So pi is super cool. It is definitionally the ratio of the diameter to the circumference in a circle. Circumference to the diameter. So it is the number you multiply by the diameter to get the circumference. They're like following that. It's probably no surprise that it shows up anytime we do circle-y stuff. It shows up in a surprising number of places. There are a bunch more things than you think ought to be circle-y stuff that end up being circle-y stuff. But I think that should be enough. I hope this was useful for you guys. Let me know if you have any questions. Feel free to swing by the math lab. We can answer questions there. Have a nice class period. Bye.